Our next speaker is Guglielmo Nocera from the Scuola Normale Superiore and Université de Strasbourg, and he will be talking about EN centers of monoidal infinity categories. Take it away.
Thank you very much. Thank you very much for the invitation. I'm really honored. So, we're going to speak about EK centers of monoidal infinity categories, but for those not comfortable with the theory of infinity categories, you shouldn't be afraid. So much of what we are going to say will involve mainly the theory of topological categories and other similar concepts. So I will be very precise in isolating the parts that are only appreciable for infinity categorists. So a couple of preliminary notations first. For us, fin star will be the category, the ordinary category, having as objects finite pointed sets and as morphisms pointed functions. The second definition I want to give before everything is the one of rectilinear embedding. So take a finite set S, and we want to build a space of functions from S copies of the open cube, of an open k-dimensional cube into the cube itself. And this will be the set of rectilinear embeddings, where a rectilinear embedding is a continuous function, which is actually an open embedding of these S distinct copies of the cube into the cube itself. So there is no overlapping. And when restricting to each copy, these are affine. So they, more precisely, they are of the form the diagonal matrix plus a translation. And the entries of this diagonal matrix are positive. So no rotations, no inversions, everything very, very rigid. And the topology we're using is the standard topology on function spaces. So the one induced by the Euclidean topology on the cube. Good. And the last remark I want to make is that a topological category for us will be a category enriched in topological spaces. And okay, for those comfortable with the theory of infinity categories, this kind of enriched category has an associated infinity category. And the construction is not very far from what one calls the nerve of an ordinary category. The nerve of an ordinary category is a simplicial set. And this is more or less what we are doing. So if you are interested, well, you start with a topological category, then you change the enrichment from topological spaces to simplicial sets, thanks to the functor that takes a topological space to its singular complex. So you pass to this version, C delta, the simplicially enriched version of the original C. And then the construction you perform is very similar to the nerve of an ordinary category. So n simplexes are functors from the from the totally ordered set with n+1 elements to C delta. However, this is not really relevant. It's just for curiosity. Good. Now we move on to our main definition. What are these EKs I want to talk about? So first of all, TEK is a topological category whose objects are finite pointed sets and whose morphisms are, well, you choose a function, a pointed function between M and N, and for each fiber, so for each J in the target, you consider the fiber here, and a rectilinear embedding of many copies of the cube into the cube itself, indexed by this fiber. And the enrichment, so the topology on the mapping spaces, on the OM sets, is induced by the topology of the spaces of rectilinear embeddings. We will see in a moment why these rectilinear embeddings are so important. Good. And again, for those comfortable with the theory of infinity categories, there is this associated infinity category, which is again the nerve of the topological category TEK. And more than that, EK is what one calls an infinity operand. This notion of infinity operand will be not necessary for our talk. But for those knowing what this is, well, then EK is actually an infinity operand, and TEK is what one calls a topological operand. Okay, we now move to our first fundamental example. So motivating a great amount of definitions. Consider a pointed topological space X and consider its loop space, omega X. Well, this space has an operation, which is given by the usual concatenation of loops. But we all know that this operation is only associative up to homotopy, and it gives rise to the fundamental group, if you want. But this operation is not strictly associative. Why? Well, just consider a rectilinear embedding from the interval to itself. So from n copies of the interval to itself. Well, then, once this is fixed, you may consider a composition law. So suppose you have 4 loops and you want to compose them. Well, then what you do is the following. You start from the base point, you remain on the base point until you hit the image of the first interval, the first copy of the interval. Then you perform the first loop, then you remain on the base point, and so on and so on. So only once this generalized partition of the interval has been fixed, you can give a strict meaning to the composition of loops. Okay, so this is where rectilinear embeddings enter. Note, and this will be fundamental for the next definition, that this actually defines a functor from the operand E1 to the symmetric monoidal category of topological spaces. To be precise, we would need an infinity categorical version of this, or at least a topologically enriched version of this. But this will be done in the next definition. For the sake of simplicity, let's just stick to the one categorical setting here, because I mean, everything is much understandable. So I will just explain the functor, not its higher coherencies, structures, and so on. Well, the functor sends a finite pointed set to the nth power of omega x, and homomorphisms, well, you should define a map from omega x to the m to omega x to the n. And how do you do this? By means of the preceding argument. So you have a composition here, which is induced in this way by the rectilinear embedding. So why am I stressing that one can construct such a functor? Because the next definition is built on this kind of situation. So in general, what is an EK algebra in a symmetric monoidal infinity category? Fix a symmetric monoidal category or infinity category. So in our example, we were considering topological spaces. More correctly, we should consider the infinity category of spaces, again, with its Cartesian symmetric monoidal structure. Or you could consider just the 2 categories of categories or the infinity category of infinity categories. These 3 examples that are exactly the examples we are going to consider have in common that the symmetric monoidal structure I am considering is the Cartesian one. So just the Cartesian product, the product of categories, product of topological spaces. This is not necessary. So the definition works with an arbitrary symmetric monoidal category or infinity category. So the role of this EK is exactly to encode the datum of k different multiplication laws on some fixed object. So before we had one law, so k equal to 1, on a topological space, omega x. And this law should be associative up to homotopy, and it was actually the case. And in case k is greater than 1, these k different multiplication laws should be distributive with respect to one another up to homotopy. What do I mean by up to homotopy? Well, it depends on the notion of homotopy encoded in the infinity categorical structure, or in general on your ambient. So if you live in topological spaces, what I am meaning is that you should consider everything up to homotopy equivalences and so on and so on. Rigorous definition, any K algebra in a symmetric monoidal category or infinity category is a functor as above, as in the example above, which satisfies this technical condition that I am not going to comment. And the main point is that with this definition, you have a selected object in your ambient category. So for example, a selected topological space, which was omega x in the example before, and so on and so on, and some kind of action of ek over this object. So omega x is an E1 algebra in spaces, because you have this associative law up to homotopy. And more in general, omega k of x is an ek algebra in spaces, because the higher dimensions allow you to make higher commutativities and many tricks that give you a higher structure. So this k different multiplication laws. This principle is called additivity theorem. So the principle that converts the datum, I mean, this definition into this definition with k different multiplication laws. Okay, so this is for ek algebras. Let us finally move to a series of examples in order to give a meaning to these definitions. So an ek infinity category for us will be just an ek algebra in infinity categories. So let's start from ordinary categories. What is an E1 category, for example? So we're moving on from topological spaces to categories. So we are changing our ambience. So the world where we are taking our examples. So an E1 category is a monoidal category. Why? Well, an E1 category should be a category with an operation. And this operation should be homotopy, associative up to homotopy. But in categories, so if you look at the mapping spaces in category, at the OM sets in a category, these are sets. There is no non-discrete homotopy notion there. So the associativity is strict. And this is actually a traditional monoidal category. An E2 category is a braided monoidal category. So you have additional structure. You have braidings, that is isomorphisms between A tensor B and B tensor A for every A and B. This is not a symmetric monoidal structure in general. So a braided monoidal category is not a symmetric monoidal category in general, because what may fail is that these braidings need not be unipotent. So going from A to B, A tensor B to B tensor A to A tensor B again will not give the identity in principle. However, if you make K grow, you actually obtain a symmetric monoidal category. And this is because, I mean, this stabilization, the fact that for K greater or equal than 3, everything is symmetric monoidal, is motivated by the fact that in ordinary categories, at some point, your mapping spaces are do not have a high homotopical structure. And from this point of view, it shouldn't surprise you that when you abandon the world of categories and you go to infinity categories, for those knowing what an infinity category is, well, then this changes. So this datum of many operations on the same category establishes commutativity rules. This is, again, an Ekman-Hilton kind of principle, but it's not enough to give a symmetric monoidal structure. These are all intermediate notions between existence of braidings, so a braided structure, and a symmetric monoidal structure on the infinity category. So, but this only when you consider infinity categories, or n categories with n greater than k, and so on and so on. Okay. So I think these two examples, these three examples, are very useful to fix what is going on. And now we can move on to the last part of the talk, which finally introduces the notion of center. So the center is some kind of ek plus 1 infinity category associated to an ek infinity category. If you think to ordinary categories, you may be willing to start with an E1 category, so a monoidal category. And this is a way to construct a braided category from that E1 category you have chosen. And this should be universal in some sense. More precisely, let C be an EK infinity category. A center of C is a final object in the infinity category of EK plus 1 algebras acting on C. So essentially, you have an EK plus 1 category or infinity category. So a braided category in the example I was saying. And this should act on C, but it should be a final object, a terminal object in the space of all possible choices of actions. So universal in this sense. Such an object exists, such an algebra exists, and is called the EK of C. And in the example I was talking about, you obtain the notion of Drinfeld center. Perhaps some of you have already heard about this. The Drinfeld center is an E2 category, a braided category, and coincides with the center according to the definition we have given in this slide. Okay. I will conclude the talk with an application because we were encouraged to talk about something having to do with our research. So these last minutes will be more geometrical in nature. This is an application to the so-called geometric Langlands program, which has in principle nothing to do with category theory, but this is of course false. Because there are many theorems in modern investigation in Langlands duality, which are formulated in purely categorical terms, in purely infinity categorical theoretical terms. So, I mean, category theory is category theory and infinity category theory is becoming very important for also for geometric representation theorists. So fix a complex reductive algebraic group. If you don't know what this is, you can just think to an ordinary group, example GLN. So GLN is the main standard example for this setting. The group of invertible matrices over the complex fields. One wants to study the category of representations of this group. So this is an abelian category, an ordinary category with a tensor product. And the theorem is the following, that this abelian category with its tensor product is symmetric monoidal and may be interpreted as a category of sheaves, essentially. So the meaning of this side, which I of course am not going to explain now, but it is a very important reformulation, which has to do with more geometric objects, such as sheaves, complexes of sheaves. And it is a very non-obvious incarnation of the so-called sheaf function principle, sheaf function dictionary, for those knowing what this is. So this is a classical theorem. It has been established in the 90s and in its more complete form in 2004, 2006. Good. So this is the classical setting, the non-infinity categorical setting. What one wants to do is to find a derived version of this theorem, because one wants to study the derived infinity category of representations. So you should understand this as an infinity categorical version of the category of representations. However, if you consider the same version, the same infinity categorical version of the right-hand side, the result is trivial and it is not interesting. So you would like to confront this direct G with something new, because otherwise it would just be, I mean, nothing new with respect to the original theorem. And what it happens, and this is the last slide, what it happens is that the technology of centers, the machinery of centers, allows you to make this connection. So allows you to give a derived version of the geometric Satake theorem, thus relating the infinity category of representations of G with something which is again very important on the other side, and it's some kind of stable renormalization, but highly non-trivial, so with new data of the category of perverse sheaves. Okay, so however, this sphere n is a new object and is very interesting on its own. It adds information to the story. Okay, and this is relevant in my research because what I have done is constructing an E3 structure here, which agrees with the E3 structure induced by the fact that, according to the definition, this should be an E3 monoidal category. So here, EK plus 1, K being equal to 2, you obtain E3. So I think my 20 minutes are off. So thank you very much for your attention.
Join me in thanking Guglielmo.